Greetings there, folks. Just back here for a very short video on using the STO3G Hartree-Fock self-consistent field algorithm for finding bond length. And this will be using the program that we featured on the YouTube videos 1 through 6 using the STO3G model. And this is just taking the results from that and then plotting them and then discovering the optimal bond length. So if you recall from those 6 videos, or go and watch them if you want to see where these numbers came from, we went through the self-consistent field method and we converged on these values that represented more or less the optimal bond length. So these 3 numbers, we've seen them on those YouTube videos, and in here they are, BX, BY, BZ respectively here. The optimal bond length, at least more or less, and electronic energy and the total energy. I mentioned in those videos that starting off with the 1.4632 bond length was a little artificial, because how would you know that? You really wouldn't know that's anywhere close to the bond length unless you'd already done a number of Hartree-Fock runs or taken some kind of measurements or something before. So we mentioned there we just used that that separation distance of 1.4632 for the purpose of illustration. So now we pretend sort of like we don't know that. So if you don't know the bond length, you want to find it, well, you have to try a number of different distances, intermolecular distances, and then calculate the electronic energy, the total energy like we did before, and then select that value of separation that gives you a minimum value. So ran the Hartree-Fock program a number of times and got lots of different values here. If you put in a bond length of 0.6 and then you run through the iterative process, when it converges, it'll give you an electronic energy of negative 5.47, and then giving a total energy when you add the nuclear separation, the Z1, Z2 over R value to it, of negative 2.13. So ran the program a number of times and just piped the numbers here into this little program. And let's go ahead and run those. So lots of different data, meant running the program many different times to get these data. So we'll just go through and chug down here to the bottom of that, and then plot the data on the computer so you can see what it looks like. So plotted nuclear separation versus electronic energy, and nuclear separation versus total energy, and here you can see what that looks like. Let's make that a little bigger so we can see it better. The top is the total energy, and then the blue point there represents the numbers we got from the YouTube videos 1 through 6 using the bond length that Szabo and Ostland used. So place that little blue dot there, and then all my other runs gave me these red dots. So that would be the potential curve, and then you can see here the minimum value is at about where the blue dot is located. The green dots down here represent the electronic energy only, not adding on the nuclear separation. So you can see what those look like here. So if you had no idea what the bond length was, you would have all these red dots. You'd have no blue dots. You'd have all these red dots, and then you would select the separation where you have a minimum on the red dots. If you look at that down here in a little more detail, a little better scaling, you can see what it looks like. Just suppose for a moment that we don't have the blue dot here. All we have is a number of successive Hartree-Fock runs giving us the red dots. Then we would select the internuclear separation distance to be that where it's a minimum. So you can see here it's not exactly where the blue dot is, but it's pretty close. And then when we do put the blue dot, the value that Szabo Ostland uses, it's quite close down there to the bottom. So the total energy is a function of internuclear distance. It looks like the way we would expect to. It has kind of that Leonard-Jones potential look to it. Of course, we have to be kind of careful when we go to large separations. These closed shell calculations may or may not converge to realistic values as the separation gets larger, but for these values here, they should be quite close, pretty good for our minimal basis STO3G. So there you go. That's what the potential curve looks like. This is how you get a Leonard-Jones type looking curve using ab initio calculations. So thank you. Hope you found it interesting. I'll see you in another video. Thank you.